All right, we're starting today with a problem that we've actually dealt with before. It's going to save us a little bit of time because we've dealt with it before. Here we have f of x equals the square root of x minus 2. Using what you know about the graphs and domain and range and all that kind of stuff, please find the domain of that equation, f of x, and then find the domain of f prime of x. And because we worked with this before, you already figured out what f prime of x was, so look back through your old work, you'll see what that equation is. All right, so first thing I'm doing is I'm looking at the domain of f of x and just to help kind of see why it is what it is. Remember that the graph of that would look like this, and it's starting over at 2. Because we cannot take the square root of a negative number, and if x is anything less than 2, notice 2 minus 2 would give us 0. If it's anything less than that, it gives us a negative. So our domain here is all x's between 2 and infinity. Notice that the 2 is included here because that would give us 0. And the square root of 0 is 0. We can do that. And so that's the domain of f of x. But now the domain of f prime of x. Well, first of all, let's make sure you found that equation. F prime of x, the equation you should have found, so you could use it on this, was 1 over 2 root x minus 2. And so that's what we're finding the derivative of. Or, I'm sorry, we found the derivative. That's what we're finding the domain of. There we go. So how do we find the domain of this? All right, so to find the domain here, well, is it going to be 2 to infinity like that? Not quite. Well, because we still have the square root in there, and our square root still cannot be negative, so it still cannot be anything less than 2. But we also have a fraction in there, and the denominator of the fraction can't be 0. I can't divide by 0 there. And what could I plug in for x that would make the denominator equal 0? 2. And so the domain of our derivative is very close to the domain of the original. The difference is that the 2 is no longer included. So it's still 2 to infinity, but it's non-inclusive. The whole reason being because our square root is now in the denominator, and we cannot divide by 0. And so one of the things I want you to see here is that when we talk domain of the original function and domain of its derivative, they're going to be similar usually, but they may not necessarily be exactly the same. And so when doing these, you really have to look at each one individually and evaluate individually what their domains are going to be. Now today's going to be dealing a lot with derivative graphs. And so domain kind of has a way of working in with some of those ideas. And we're going to do 3 of them together here, and then you're going to do some on your own. We're going to start with this one, and I think you should probably write these down on your paper as we do them so you can look back on them and use them as a reference if need be. Now if we're going to sketch the derivative function of this, we have to of course remember what derivative is meaning. Remember the derivative is the slope of the tangent line. Now if I'm looking at this first one, at any point along this first piece, it's linear. So the slope is actually constant on there. Our tangent line at any point along that particular piece would be the same line. So it's all going to have the same slope. That's the nice thing about starting these types of problems with something that's linear pieces, like these, is the slope is going to stay the same throughout that particular part. So what is the slope of that first piece? It is 2, because we're going up 4 and over 2. And remember, of course, delta y over delta x. How far we go up over, how far we go over. Okay, what is the slope of this middle piece? 0. Yep, if it's horizontal, it is 0. And then what is the slope of this last piece? It's going over 1 and down 4, so yes, it is negative 4. So those are really the piece of information I need to know in order to be able to sketch this graph. So I set up a new graphing grid, and so that's what you want to do on your paper, so you have a place to copy the derivative graph. And now I can start graphing that derivative. So remember that we started with a slope of 2, and the derivative is slope. So when I go to graph this, it's going to be at 2. So I'm going to go up to 2 here. And so my graph is just horizontal along at 2, because the slope is a constant 2. All the way between 1 and 2 here, my slope is the same. All right, now I look to see the next piece. And remember, the next piece was here where the slope was 0. So that's between 2 and 7. Now, if our slope is 0 there, that means my graph is going to be a horizontal segment again that's at a height of 0. Because basically, the equation of the derivative here would be y equals 0. Just like the equation of the original would have been y equals 2. That's why they're horizontal. And then for the last one, remember we had a slope of -4. So then when I graph the derivative, I'm really graphing for that piece y equals -4. And so that one starts at 7, goes to 8. Oops. So it's just in here. And so you can see there we're actually figuring out, okay, this is our slope, and so I'm just plotting the slope. It's constant throughout those pieces, so that's why they're just horizontal. But now we got to tweak something else in here. Because this graph is pretty darn close to being correct, but it's not actually technically correct. Because what is the actual derivative at 2? Because the derivative from the left we can see was 2. The derivative from the right is 0, but they're not the same. And so the derivative then at x equals 2 here actually does not exist. And so for that reason, on our graph, we should have open circles here at 2. Because the derivative at 2 doesn't exist. The same thing happens up at 7, because we have another corner on the graph there. So we should have an open circle and an open circle for both of those ends at 7. Now, just like corners, we are also going to end up with the same kind of situation happening at the ends. Because at the ends, we can see that the slope coming from the right is 2, but from the left, there's nothing here. Same kind of thing happens at this end. So we also put an open circle at the other ends. So any place where you have a corner or an end, you're looking at open circles in the graphs. One last little detail here. What does this graph actually represent? So it was the derivative of our original equation. The original equation, notice, was talking about displacement over time. If we take the derivative of displacement over time, what's that give us? Well, it's still going to be about time. But the derivative of displacement just means the same kind of idea as like position or distance. They're slightly different, but they're all interrelated. Yep, it is velocity. So what we actually just graphed was the velocity of this, because displacement is just talking about how much it's moved over time. And so the derivative is telling us how quickly it was moving at each of those times. So really what we just graphed was the equation v of t. All right, now we just saw one case where f was not differentiable. There's a few different ones that I do want to take a look at and make sure you're aware of. Different situations where if you look at the graph, we cannot find the derivative. The first of those is a corner point. That's the one that we just saw. So if we see a corner as part of our graph, it's basically going to come up in piecewise functions. Actually, pretty much all these do. Then we cannot take the derivative just at that one point. Of course, we can still take the derivative at other points. Okay? We cannot take the derivative at a discontinuity. Now, this example is a jump discontinuity. The same would be true for a removable discontinuity. We cannot take the derivative at that. And then the last situation is that if the tangent, when we drew it in, was vertical, we also cannot take the derivative at that point because derivative is slope, and the slope of a vertical line is undefined. All right. Now with that in mind, here is a new graph. I'd like you please to sketch the derivative function for this one. All right, and so let's actually take a look at how we would sketch the derivative of this function. So first of all, again, I look at each of the pieces individually, and thankfully they are all linear still. We're going to be focusing on the linear parts today. The first part, we're going up 3 and over 2, so this has a slope of 3/2. So we know that's basically the equation y equals 1.5. So from 0 to 2, it's going to be up at 1.5. So I can go ahead and go open circle, because of the corners in the end, and do that up at 1.5. All right. Then from 2 to 4, so here's 2, here's 4, our slope here is 0 because it's horizontal. And so then, again, open circle at each of the ends and connect those. All right. The next segment goes between 4 and 9, so I'm going to put my next mark down there at 9. And then that's a negative slope. More particularly, if we count how far down and how far over it goes, we can see the slope is actually -1. So, go to -1. Open circle from 9 until, from 4 to 9. And so it's a constant slope of -1 through there. And finally, from 9 to 10, it's horizontal again. So that has a slope of 0. So between 9 and 10, open circle, and then the segment is just up at 0 the entire way through. So that is the slope of your derivative. And this graph, notice, was labeled as time versus position. Well, if I find the derivative of position, what's it give me? Once again, it gives me velocity. Then we're now going to do one last one here together. And so sketch this original graph, make a quick sketch of its derivative, and then we'll actually walk through that derivative together to make sure you're thinking along the right lines. All right, then let's take a look and see, and one thing to be aware of here, if you're like me, when I did this problem the first time, I was in the habit of seeing these all going up by 1s, but notice we're not going up by 1s on our vertical, we're going up by 2s, and so that's going to affect our slopes. So between 0 and 2 seconds here, our slope is going down. So we know it's going to be negative. What is the actual slope there? So I know I'm looking at something like that. It's just a matter of exactly what it is. It's a -2. And so I can go ahead and label that as -2. The next piece of this piecewise function goes from 2 to 4. And on that section, it is horizontal. So again, corners mean open circles. And then since it's at 0, I just draw my segment up at 0. And then between 4 and 6, we have our last part. And between 4 and 6, our slope ends up being 5. Even if I didn't know it was 5, I could still sketch it in as a big positive number up here. But since I do know exactly what it is, I can go ahead and label that as being up at 5 there. And so then this is our graph of our derivative. Again, it's showing, since this is displacement, velocity versus time. So it's showing us how fast is this object actually traveling at each of those times. So next up, we're going to do a worksheet. I'm going to give you the worksheet. You're going to be given a number of position graphs. Then you're going to sketch the derivative of that. And then we'll compare them up here together. So here's what your first 3 answers would look like, just so you can kind of make sure you're on the right track. Now, I am assuming that at the ends, those mark places where it's starting and ending, and so I used open circles at those. You can leave out those open circles if you were thinking it was continuous, but these must be open circles here where we have a corner, because we need to be showing that that point is not included. We can't find the derivative of that one. Okay, here's your second set of answers. Answers for numbers 4 through 6. All right, now numbers 7 through 9. Check each of those. 7 through 9 sometimes is a little bit tricky because you notice they're all decreasing all the way through, which is why we get our answers the way they are. But some people get thrown off, especially by this last one, where they look at it and they think, oh, well, part of it's positive, part of it's negative. Yeah, but remember, we're only looking at the slope, and the slope stays negative. We don't care about what the position is being positive or negative, only the slope part. And here's the last set of answers, so you can check those as well.